The universe may have never begun, physicists say. They're saying in the beginning there was, well, maybe there was no beginning. Perhaps our universe has always existed, and a new theory of quantum gravity reveals how that could work. Paul Sutter, Live Science on Science Alert. Reality has so many things that most people would associate with sci-fi or even fantasy, said Bruno Bento, physicist who studied the nature of time at the University of Liverpool in the UK. The nature of time, okay. In his work, he employed a new theory of quantum gravity called causal set theory, in which space and time are broken down into discrete chunks of space-time. At some level, there's a fundamental unit of space-time according to his theory. Bento and his colleagues used this causal set approach to explore the beginning of the universe. They found that it's possible that the universe had no beginning, that it has always existed into the infinite past and only recently evolved into what we call the Big Bang. A quantum of gravity? Quantum gravity is perhaps the most frustrating problem facing modern physics. We have two extraordinary effect theories of the universe: quantum physics and general relativity. Quantum physics has produced a successful description of three of the four fundamental forces of nature: electromagnetism, the weak force, and the strong force, down to the microscopic scales. General relativity, on the other hand, is the most powerful and complete description of gravity ever devised. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. But for all its strengths, general relativity is incomplete in at least 2 specific places in the universe. The math of general relativity simply breaks down, failing to produce reliable results. In the centers of black holes and at the beginning of the universe is where it breaks down. These regions are called singularities, which are spots in space-time where our current laws of physics crumble, and they are mathematical warning signs that the theory of general relativity is tripping over itself. Within both of these singularities, gravity becomes incredibly strong at very tiny length scales. As such, to solve the mysteries of the singularities, physicists need a microscopic description of strong gravity, also called a quantum theory of gravity. There are lots of contenders out there, including string theory and loop quantum gravity, and there's another approach that completely rewrites our understanding of space-time. Causal set theory. In all current theories of physics, space and time are continuous. They form a smooth fabric that underlines all of reality, of course. In such a continuous space-time, 2 points can be as close to each other in space as possible, and 2 events can occur as close in time to each other as possible. But another approach called causal set theory reimagines space-time as a series of discrete chunks or space-time atoms, and this theory would place strict limits on how close events can be in space and time, since they cannot be any closer than the size of the atom. Can we stop time? For instance, if you're looking at your screen reading this, or looking at this video, everything seems smooth and continuous, but if you were to look at the same screen through a magnifying glass, you might see the pixels that divide up the space, and you'd find that it's impossible to bring 2 images on your screen closer than a single pixel. This theory of physics excited Bento. Bento said, "I was thrilled to find this theory, which not only tries to go as fundamental as possible, being an approach to quantum gravity and actually rethinking the notion of space-time itself, but which also gives a central role to time and what it physically means for time to pass, how physical your past really is, and whether the future exists really or not." Beginning of time. Causal set theory has important implications for the nature of time. Bento says a huge part of the causal set philosophy is that the passage of time is something physical, that it should not be attributed to some emergent sort of illusion or to something that happened inside our brains that makes us think time passes. This passing is in itself a manifestation of the physical theory. So in causal set theory, a causal set will grow one atom at a time and get bigger and bigger. The causal set approach neatly removes the problem of the Big Bang, singularity, because in the theory, singularities can't exist. It's impossible for matter to compress down to infinitely tiny points. They can get no smaller than the size of a space-time atom. So without a Big Bang singularity, what does the beginning of our universe look like? That's where Bento and his collaborator Stav Zalel, graduate student at Imperial College London, picked up the thread exploring what causal theory, set theory has to say about the initial moments of the universe. Their work appears in the paper published September 24th to the preprint database ARXIV, and the paper has yet to be published in peer-reviewed scientific journal. Bento said the paper examined whether a beginning must exist in the causal set approach. In the original causal set formulation in dynamics, classically speaking, a causal set grows from nothing into the universe we see today. In our work instead, there would be no Big Bang as a beginning, as the causal set would be infinite to the past, and so there's always something before. Their work implies that the universe may have had no beginning, that it has simply always existed. What we perceive as a Big Bang may have been just a particular moment in the evolution of this always existing causal set, not a true beginning. Not a true beginning. There's still a lot of work to be done, though. It's not clear yet if this no beginning causal approach can allow for physical theories that we can work with to describe the complex evolution of the universe during the Big Bang. One can still ask whether its causal set approach can be interpreted in a reasonable way, or what such dynamic physically means in a broader sense, but we showed that a framework is indeed possible, Bento said. So at least mathematically this can be done. In other words, it's a beginning. And now NASA animation of the Big Bang and explaining of how the universe is and the universal dust and things that have to do with after the Big Bang event. And this was from Live Science, the original article. It's on Science Alert. Please leave your comments. Thank you for your support.
The Large Magellanic Cloud is among the closest galaxies to our own Milky Way, offering astronomers a detailed look at what makes a galaxy tick. One of its most striking features is the Tarantula Nebula, a star-forming region more active than any in ours or other neighboring galaxies. This is the source of most of the gamma rays we see from the LMC. Astronomers have thought the emission was a byproduct of star formation, which includes short-lived massive stars whose explosions produce shockwaves that can accelerate particles. Interactions by these particles, called cosmic rays, can produce gamma rays, the highest energy form of light. But a discovery by NASA's Fermi Gamma Ray Space Telescope has turned this thinking on its head. Most of the emission arises from a single gamma ray pulsar, the first ever detected in another galaxy. Pulsar J0540-6919 turns out to be the most luminous gamma ray pulsar yet observed, beating the previous record holder, the famous Crab Nebula pulsar in the Milky Way, by 20 times. Discovered in X-rays using NASA's Einstein satellite in 1984, J0540 looked like a twin of the Crab until Fermi's Large Area Telescope unveiled its gamma ray power. While Fermi is the most sensitive gamma ray telescope ever launched, its vision is not as sharp as telescopes using other wavelengths. In 1998, NASA's RxTE satellite detected X-ray pulses from J0537-6910, a pulsar located just 16 arc minutes from J0540, or about half the apparent width of the Moon. In the early years of Fermi's mission, the two pulsars were seen only as a single steady gamma ray source. But the vision of Fermi's Large Area Telescope improves over time for two reasons. First, it collects more gamma rays, and each one adds to the story of cosmic sources. Second, Fermi scientists improve their knowledge of the instrument, allowing them to reanalyze existing data to tease out more detail. Thanks to new data and a reprocessing of old, Fermi scientists were finally able to detect gamma-ray pulses from J0540, revealing its incredible luminosity. The object is responsible for perhaps 60% of the gamma rays from the Tarantula Nebula. The surprise that it's the pulsar, not the nebula, suggests astronomers need to revisit their understanding of how cosmic rays are produced and move through star-forming regions. And the best way to do that, of course, is to keep watching the sky.